Okay. And shoot me an email later on. I put my contact information in the chat window if you would like to get the link to the recording, as well as if you would like to get a copy of the presentation. And today's webinar will go through how you can set up and model a small electronic system for thermal analysis. The idea is just to give you a feel of the flow. In practice, your system may be a lot more complicated, which we can model those. And if there are questions about particular features or anything that is weird in your system that you would like to know, we can model. Please contact me, and I'll be glad to engage and discuss with you for your particular requirement. Okay. Also, you can enter any questions you have in the chat window, and I will try to pause regularly to try to entertain those questions. Okay, so let's begin. So first of all, EDA Direct, we have been the authorized distributor for Mentor Graphics since 1997, and we have helped customers in the high-tech industries with EDA tools, training, workshops, and in some cases, services. This is just a short list of the vendors that we sell tools for and support. So who are the companies out there that uses FloTHERM for electronic system cooling analysis, thermal analysis? This is just a short list to show you many of the major companies out there. You can see big system server guys, networking guys, consumer products, even some of the manufacturing computers. So these guys are actually using FloTHERM for thermal analysis in the product. And the survey that we had basically is that a lot of the users out there who use FloTHERM continues to use FloTHERM. And again, you will see more of the market segments out there. You see consumer, Black & Decker, AEG, Watts, Motorola. So lots and lots of people out there are using this tool. The problem statement that I want to state here is that given the technology trend, where as time goes on, the complexity of electronic circuits gets more complicated. Not only you have smaller and denser chip, but you will have smaller boards and system thermal power, power consumption of system also in many cases exceeding hundreds and thousands of watts. Okay, that's on the one end. On the other end, you may have a smaller form factor system, Bluetooth headphone, little cameras, security cameras that are small, but nevertheless, the thermal can be an issue because of the power density. That is the power consumption per unit area. Okay, so we are actually seeing a trend in the thermal issues. And here basically just show you that the law that every 2 years or so the chip size double, things like that, the Moore's law. The thing to take away from this is that the power density or the watt per centimeter square of some area square increases, and that poses a challenge. And in some application, for example, in this case is a rugged board, design CPU board, customer have to resort to extensive heat sink implementation, heat block metal, lots of things, which takes up space, increases the weight, increases the cost for the system. So that's really some of the solution out there. Okay, so in terms of positioning the tool to address a particular customer need, there are a couple areas to consider. So the first area of focus is we are looking at engineers who call themselves as thermal specialists. These guys are really looking at heat issues all day long. and they could be an electrical engineering background or mechanical engineering background or neither, but their focus is really to look at this heat issue. And so the product for that is the FloTHERM, okay? And then on the other hand, you may have engineers who have mechanical background or mechanical designers who design mechanical assemblies, enclosure, chassis, more mechanical inclined. They like to stay within that mechanical environment, and doing thermal analysis is just part of the job. That's not the main focus. And for that, we have a product called Flow EFD, which are more mechanical friendly, mechanical environment friendly. And then for cases where you have a mixture of both, where you may be an electrical engineer, maybe a mechanical engineer, maybe a little bit of both, your design might be complex with complex structures. What I mean by complex structures include things like round shapes, fan blades, motors, things that are round, not necessarily rectangular. And we have a product for that, and it's called FloTHERM XT. So we found that there isn't one product that fits all, depending on where you are leaning, or your background or your preference. We can specify the correct product for you. Now, all three can do electronic cooling system thermal analysis. Okay. So the kind of industry verticals or market segments that can use thermal analysis, including, not in any particular order here, but in the aviation industry. So if you take a look at a typical plane structure, you will see fans, you will see heat exchanger, you will see, electronics inside there. You see lighting, you see pumps, you see valves. So a lot of stuff, a lot of mechanical as well as electrical in the aviation industry that do need the capability of doing thermal analysis. Then you get to the automotive side of things. And inside the car nowadays, especially with all those hybrid batteries and infotainment centers, you have a lot of electronics, you have motor controls, you have the engine, the heating, you have the pumps, you have the brakes, aerodynamic headlights, and all that stuff. So those will also require thermal analysis. And then you get into the electronic computer servers market segment, and this is just a representation of the kind of boxes out there. Tesla guys may have systems that are big, huge, slot-mounted ATCA architectures and all that stuff. But this is just showing, what you can find within, let's say, a PC, a server, a computer, and you will definitely see PCBs. You see lots of chips. You might see, cooling, water cooling, liquid nitrogen cooling. You will see power supplies, heat sinks, fan cooling, even rack-mounted boxes can be represented like this. So a lot of electronics, more electronic here, more so than any mechanical or moving component. Maybe the worst case in here, you might have a cold plate with liquid nitrogen, but the rest is pretty much electronics. Okay, so that's in the electronic segment. And then even for building structure, there's different types of thermal analysis. That's AC cooling for the room and things like that. For the factory, definitely you have pumps, valves, electronic controls, lots of things in there. And then let's see what else here. Oh, and then in the home, for the home case, you will have your, range oven, more electronics nowadays, lightings, fans, stuff like that. Okay, so we are in all the CFD industry vertical. So CFD stands for computational fluid dynamics, where we will model heat flow as fluid and air particle as fluid. And by studying the heat flow, we can see the effects where temperature rise and falls and be able to predict very accurately where the thermal issue might be. And based on those, whether you're in any one of these vertical segment or market segment, will be able to give you a view of where your problem is. And then you can decide how to mitigate the problem. Okay. Uh, Looking at one step deeper, we have a complete thermal analysis solution ranging from chip design. If you are in this area where the concern might be, hey, I'm looking at the substrate, I'm looking at the packages, I'm looking at the bonding, the material, encapsulants. Should I have a heat spreader? Things that are related to chip design from a thermal standpoint, we have a solution for that. And then moving onward to the board design, where you will see a majority of the electrical engineering guys be looking at board layout, board placements. This is an area where you may not be concerned with the type of boxes where this board will end up, right? You might be designing a network card, something that might be plugged into another box somewhere else. So the concern here would be how would I have a best placement for my electronics? How would I run some of the cables? How should I have some heat sink on the board? And the focus is really more on the board side of things. Okay, we have a product for that called FloTHERM PCB. And then as you get into the system side of things, this is where you would be in some sort of enclosure. And an enclosure can be a simple one, like the case of a security camera, like a router, small set-top box, maybe even a laptop, things like that, right? And but it has some complex structure, curvy surfaces, rounded edges, blades, things like that. We have a product for that. And moving forward to the bigger system where it may be rack-mounted device, multiple card chassis, things like that. So the idea is we can analyze everything from chip, board to system. Okay. So let's look at the effect of the heat. Where does it start and where does it end? So most likely you will see that it comes from the surface of an IC. An IC could be an RF diode or power supply, so some component transistor. So it comes from the IC, and the heat can be conducted away, can be radiated away, or can be air cooled. Okay, so the idea is really the hot part will move toward a colder or cooler area. That can include the ambient. It can include the surface where the chip is mounted, or can be air cooled. So in that path, it can encounter various type of objects and obstructions. So objects that are beneficial would be heat sinks or heat spreader. Obstruction could be the cabling running over the chip, blocking the airflow of a fan, right? So those will be obstruction. So there are three ways where heat can escape or move from the problem area. One is conduction, and that's basically surface, surface to surface heat transfer. Convection would be air flow, cooling, and things like that. And radiation, it will act like a heater. It will radiate the heat out. And in certain environment, you may have one or the other or all, right? So, for example, in space environment, there's no air. So definitely the only way you can relieve the heat is through conduction and radiation. Um, so things like that. And it will radiate the heat, move the heat out from the chip to the board. And the board material is not necessarily the best material for heat relief, but nevertheless, it can move there, and the board can be put into a box, right? And the box can have other cooling component in there, including airflows, and eventually it ends up, you know, the Earth standpoint. We won't go beyond that. So how easily the heat find its way to the ambient determine that temperature rise, and we can certainly predict that through the through modeling the component, the enclosure, the chassis, the environment, the gravity, even solar effects. Time of day, we can predict where the sun would be, and that kind of thing. And in that process, we can look at all the points that can contribute to that heat issue. Okay, so now let's talk about the categories of electronics cooling. So if you, I'm gonna see if I can mute some of you. Okay, just want to make sure I don't mute myself here. Okay, all right. So in the categories of electronic cooling, uh, you might be focusing on some area. Just because you have an electronic system, it doesn't mean that all the areas are important for you. So for example, you might be designing a chassis where you are looking at the fan sizing and placement. How big would my fan be? Should I double stack them? How many should I have? Where should I place those? Should I place on the top, bottom, on the side? Blah, blah, blah. So sizing and placement, that can affect the airflow inside your system. Okay, so that could be a concern, right? You might not be designing the chassis, but you're looking at implementing the fan. You might be looking at designing a custom heatsink for your particular board, particular chip that has a very specific requirement where it will dictate a custom heatsink design. And what is the advantage of, well, first of all, here's the problem statement with the heatsink, is that when you first power on the system, it is cold, cooler, and so the heat flow, the airflow will be different. And as the system powers up and start running, it will affect the flow of the air inside the box. And that also affects how the heat flow. This is what we call the wake effect of the heat sink. And depending on how you design your heat sink, how many fin, how many blades, what's the thickness, what's the height, what is the material, it can alter the airflow in your system. Okay, so instead of going through prototype designs of heat sinks where you may have to wait weeks for the heat sink to come back, and if it meets your criteria, that's great. If not, you have to repeat all that loop again. So why not simulate that structure, and not only simulate the design that you have in mind, but find an optimum design, right? Too big is not good. Too small is not good. What is the right size for my design based on my uh, area and volume requirement? Okay, so heat sink design and selection could be more of a focus for you. And then if you are looking at designing the chassis, okay?
Oh, should we go there? No, we try to, yeah, computer transfer first. I even though working, I gave you the
Okay.
copy.
I'm gonna mute that. So please make sure you mute your microphone to minimize the background noise for everyone else. Okay, so back to the vent sizing and location. So you might be designing a big chassis, a rack-mounted system, where you want to look at where should I have the vent? Should I have it on the side? Should I have on top, bottom? What are the opening free air ratio to really maximize the recirculation of the air flow inside your system? Okay, so vent sizing location could be a criteria. Um, and then if you are electrical engineer and you're doing a board design, the main concern would be the placement of your ICs. From an electronic standpoint, you want those ICs to be as close as possible to maximize the signal integrity between the chip. But from a mechanical standpoint, that's a very bad idea. The closer you have, the chip to one another, the more the heat is going to be focused on that area. And so you want to be as far apart as you can. But the EE guys want the chip to be as close as possible. So what is the final solution? That's where you run the simulation and see thermal simulation and see where the best location would be. And you would also run a signal integrity simulation to see how far you can be, okay, to maximize your signal quality as well as minimizing your thermal issues, okay. Um, and then in some cases where you might be concerned with things like trace heatings, you may not be aware of it, but it doesn't have to carry a lot of current. Sometimes you may have a bunch of differential pairs running things at high speed, gigahertz, gigabit rates, and you're bunching up all of those together in a small area, and power is proportional to the square, to the frequency. So you may have local trace heating effects on your signals, not just on your power lines. And you might want to see those trace effects, and we can do that, okay? And that's called Joule heating. And then in cases where you want to understand about the case and junction temperature prediction, right? You're trying to figure out what's the best package to use, whether or not you use heatsink or not. You may or may not be the chip provider. You might be using the chip, but you want to understand that case and junction temperature. Might be using an RF diode, right? So the surface area is very small, but the power density is very high. Okay. So how do I predict the heat effect from that RF diode on my board? Back to enclosure and thermal design. How big should my box be? Obviously, from a thermal standpoint, you want to be as big as possible, but from a practical standpoint, you can't have that. And then how dense should I have my board inside the system? Where should I place my power supply? How would I run my cable? What are the vents and sizing, that I need, right? So, and then in some products, the touch temperature might be important. So let's say you have a cell phone design, right? You don't want the touch, the touch temperature of the case is important. If your product is a Bluetooth headphone, right? You don't want the headphone to heat up and pressing against the skin. So in some product, touch temperature is important, and in some it is not. Okay. So what kind of material should I use? How big should it be? And blah blah blah. And then back to the package design, as I mentioned earlier, you might be concerned with the bonding wire, substrate materials, heat spreader, you know, fuse LEDs to die path, things like that. Okay, so from a chip standpoint, it is also important because if you don't relieve the heat of the chip, the electronics will be affected and the functionality will be affected. Timing will change. Things will slow down or speed up depending on the thermal content. Okay. So what makes a difference in the FloTHERM product that we have? And one of the main challenge is for customer who are doing thermal analysis is how easy it is for me to set up some scenario. I don't want to spend a lot of time learning, creating parts, okay, and not being able to run simulation. The way we help with that is it comes with a small parts library. What do we mean by small parts? Small parts are commonly used components, heat sinks, fans, thermoelectric coolers, even PCBs, um, components that are already defined in the library, which you can drag and drop, resize them. This is the first order estimation. So the flow is, should I wait until I get all my mechanical design done, or can I just go ahead and model things already if I know all the sizes, location, and things like that? So the answer is yes, and that's because we have these small part library, and not just some temporary and generic part. For example, when we say we have fans, we actually have the actual fan part number from the manufacturer. You can drag it and put it down, and we will know the fan curve of those components, right? So those are exact model. Okay, so that's number one. So the bring up and modeling from scratch is very easy. Okay, and as you design something and simulate something, you can save those off as library components for reuse later on. Okay, so the time to come up to set up the model is quick. Secondly, we are we have seen that once you have these components in place, it is a matter of moving things around and trying to find the optimum location and have the solution. And that often involves in gridding and meshing. Okay. And with other competitive tools out there, we have seen that users spend a lot of time in meshing, remeshing to make sure that they have the optimum grid sizes to get the most accurate result, but not spending too much time. Okay. So one of the advantages that we have is the actual it's actually automated. So if you analyze a component, it will have its own grid structure, and as you move that component around on the board, for example, we automatically merge and mesh the boundaries between those. You can always come in and fine tune those, but the automatic meshing and remeshing is done, which will save you hours and days of work and help you to converge to a solution a lot quicker. So, rather than spending a lot of time meshing and remeshing, you will be spending time looking at topologies and solutions. Okay? And then on top of that, we have a thing called parametric sweeping. So, for example, you can specify the parameters to the tool. Okay, my fan can be in this location or that location, anywhere in between. The spacer of the board can be this much. The thickness of the heat sink can vary from 10 mil to 50 mil, 100 mils, or well, whatever that range is. So give all these physical parameters and let the tool go through and sweep them, right? Go through all the possible combination. And as it goes through, you will specify that, hey, whatever you do, make sure that the location, the temperature at this particular location cannot exceed 70 degrees, 60 degree, or whatever that number is. And it will go through all these permutation and will show you all the possible solutions that meet that criteria. And then you would come in and say, hi, I can't have it over here. I can't have it over there. I'll pick this solution. So it relieves you from setting up all of these scenarios, and it gives you that option of just picking which solution is best. So that would save you a lot of time in thermal design. And then we have a very powerful visual editor that allows you to look at things like the bottlenecks, where the heat is concentrating, as well as looking at cooler area where you might be taking advantage. You can take advantage of those areas to implement your solution. Okay, so very photorealistic visualizations of the results. Okay, we have cut planes X, Y, and Z. You can slide through the design, whether it's a chip or the board or the box, and be able to look at all the temperatures on that plane. Okay, I'll show you a little bit more later in the demo. Okay, so what does the FloTHERM workflow look like? What do I need to do? What does that look like from a high level view? So what you will need is you will need to bring in your mechanical assembly, right? Bring in your mechanical design, whether it's chassis, box, PCBs, structure. That's on the EDA side. But motors, fans, all your mechanical designs, assembly, you can bring it in to the environment. And on the other side, you will bring in your PCB board. Okay. If you are using Mentor Graphics layout tools, we can actually export out the thermally friendly file that can be brought in for thermal analysis. if you use other tools out there, Cadence, Allegro, other PCB, we can bring in, ODB++, we can bring in IDF board, so files. So we can bring in those EDA files, bring in those mechanical files, and then the idea is to manipulate. Okay, and what do I mean by manipulate? Manipulate means you can change the materials, you can experiment with different thermal loads, you can play around with gridding, um, you know, gravity, environment, adding stuff, replicating the board, things like that. So manipulate and solve. Okay, and then in some cases, you can actually create geometry from scratch. So, for example, you may not have the board done completely. You can actually go in and create those components from the small part library that we have. So you don't have to draw each and every single resistors and so on and so forth. But you can pretty much create very accurately what components are there. Okay, so you create the geometry, you assign the boundary condition. Okay, it is in ambient, it is in convection, airflow, blah, blah, blah. And then the tool will use the Navier-Stokes equation to solve, okay, to look at the CFD, airflow, particle, and then we can analyze the result, whether you do it manually or you can do it, parametric sweep, and basically you will loop around this area until you converge on the solution. Okay, so that's basically the workflow and what it looks like. Okay, let's talk about how do we bring in a board file. Okay, what we have is we call it the Flow EDA bridge, and this allows import from PCB tools, whether it's Graphics, Cadence, Zuckens, or other format where you can bring in as IDF. So, for example, Cadence Allegro, we have a plugin. Uh, you install that plugin, and when you're done with layout in Allegro, you press that button, and it will generate a FloTHERM file. It works right inside Allegro. Um, Zuken, same thing. We can also bring in ODB++ file uh, to model the board. Okay. Once you bring it in the Flow EDA bridge, we need to do some massaging. And what that means is if you have models, thermal model for the chip, you may have a big FPGA, you may have an Intel processor, uh, there may be FloTHERM model for those. You want to replace those components with the thermal model. Okay. You might want to assign some power consumption number for the device. U1 might be 5 watt, 2 watt, things like that. You have to add to the picture. And then that's basically it, And here you can also try to add some heat sink. You can also look at the layers routing. Okay, look at the trace effects, trace heating effects in here. Okay, so, and then once you're done with this, and you bring that final model into FloTHERM. So you will do this for the PCB side. And then on the mechanical side, there is a Flow MCAT bridge. What that does, it will take in the mechanical files format. Okay, we support natively SolidWorks, Pro-E, Creo, Cadia, or you can generate the neutral file, step file, SAT file, IGES, DXF file. Bring these assembly into the bridge. Okay, then we're going to do some simplification. We're going to do some decomposition. So simplification means I'll show you more in the demo, but let's say you have a rounded edges like this, which are thermally insignificant. In many cases, we could convert those into square structure. You may have some venting, and we'll replace that section with an equivalent thermal model that have the same free air ratio that you have. Things like that. We simplify things to make the computational easier. And then you bring it into the FloTHERM environment. So basically, you have to dissect each one of those layers one at a time. Okay, and then for the visual editor, once you run the analysis, you can visualize the airflow, the air particle flow. You can do a cut plane, cutting through the component board system. We do a surface plot, and we also can cross probe to the table view, to the assembly view, so you can check, select a component in the assembly, and the thing will highlight in the visual editor, and you can rotate, you can measure, annotate, all that stuff. Okay. I mentioned earlier about parametric sweeping, and that is done through the thing called command center. And in the command center, this is where you will specify the variable. The variable means, the locations of a certain structure, the size of certain structure. I can vary the fin of the heat sink from this thickness to that thickness. I can vary the height of the heat sink. I can vary the location of the fan. I can vary the opening of the vent. Um, all of those, you can tell the tool that go ahead and sweep on these variables, and it will go through all of those one at a time and do all the computation and show you the final solution. Okay. Um, and also, FloTHERM does not work just by itself. Mentor also has the hyperlinks power integrity software. This allows electrical engineers to go in and look at the board layout, look at the power plane, look at the decoupling on the board, and analyze the board from a power integrity standpoint. Do I have enough copper traces? Can it carry enough current? From an electrical standpoint. Those results from hyperlink can be exported and brought in and bring into FloTHERM for more accurate analysis of the system, okay, where the board is now a component of the chassis of many other boards. We can actually leverage those PI results in the thermal analysis results, okay. All right, so in summary of the FloTHERM, we have the advantage where there is a predefined object, and those are the small parts that allows you to easily create a system and be able to model a system before the board is done, before the mechanical assembly is done. You can, do all of that from scratch. Number one. Number two, there are libraries of standard components out there, fan structure, text, cooling, heat pipes. Bring it in, be able to model those. Okay. Mechanical import as well as PCB file import. Okay, so those are the main thing. And then, we have a very fast and robust solver. The FloTHERM technology was acquired from a company called FloMerix back in 2008. And the technology has been around for more than 25 years. Standards out there. So pretty powerful visualizations of the results. You can do surface, temperature, airflow, particle. We can animate the flow, things like that. And then last but not least is the ability to do parametric sweeping. Okay, this is very useful if you're doing heat sink design. If you want to look at placement of ICs, should I have a baffle? What is the angle of my baffle? What is the size of that? Okay, so all of those scenarios can be set up. Okay. And here is our contact information. And please, check our website for upcoming webinar, seminar, workshops. We also have video recordings of many of our tools. So FloTHERM will be up there. If you want to look at layout videos, we have those. You want to look at signal integrity, power integrity, we have all those on our website. Okay. So before I jump into the demo, any general question or particular question that you may have based on what you've seen so far? So please unmute yourself if you have any question. Okay, and if not, let me just start up the tool. So the latest version that we have is 12.1 that was just released in April. And when you bring up the tool, you will see this kind of environment where you have four windows. This one where the Y is orthogonal in front of you. This is a 3D view, and this is where the Z is orthogonal to you, and different three view, including the 3D view. And you will have a navigation window, and on the left, we'll go through some of this button later on. So let's say I want to create something very quickly and I want to run a simulation. How do I do that from scratch? So this is what we call the root assembly. Okay. So first of all, you have the system. The system contains the computational domain. This is the area or the volume, if you will, that contains your design. And all the analysis will be done within this box, this volume. So certainly you can resize this to make it smaller or bigger. So obviously you want the volume to be as small as possible to minimize the computational time, but you also want it to be as big as possible to to cover things that are outside your design. Okay, so for example, anyway, so we go to the root assembly. So the most basic component is a cuboid. So all I need to do is basically say I want to add a cuboid. So now it added into the system with some coordinate. I will select that and I will say I want to specify the position of this cuboid. And first, let me change to the unit to millimeter. Okay. So now let's suppose we have something 250 millimeter by 250 millimeter by 100. Okay. And let's say the position of this is 500 by 500 by 100. Okay, so I just created this cuboid, okay, and that is the structure, and that's the size and location. Okay, you can certainly use the graphic, the GUI to resize it right here, move it, expand, things like that, or you can be specific with a particular number. Second thing I want to do is I want to attach some sort of material to this. How do I do that? So select the attachment tab. In the material section, right now there's no attachment, so I can say I'm going to load the material from the library. Okay, so select this, and the library comes up, and in here we have lots of materials. We have alloy, carbon, metals, plastic, resin, all that thing. So what we'll do is we'll select metal, and we'll look at aluminum pure. Okay, so select that. Now aluminum pure is assigned to this piece. Okay, and let me add another piece again. Okay, so go back, add another cuboid. But notice you can also add, here's a PCB I can add. Here's a fan I can add. Here's a cooler. There's a heat pipe. Here is tech, right? Thermoelectric cooler. So a bunch of things I can add very easily. In this case, I'm just going to add another cuboid here, right? And then let me assign the location for that. So first, let me change the unit to millimeter. Okay. So position would be, let's say 450, 450, and let's say 200. Okay, stuff like that. Okay, so I put a second material piece right here, and let me assign a material to that. So you can go back to the library like before, or you can choose some commonly used material, including copper FR4 material for the board, for example. So let me use copper, okay, for that. And then let me assign a thermal load. Okay, so what we do is we say into the thermal, there's no attachment. Let's create a new thermal load model. Okay, and let's call that something like 500-watt component. And the heat will be conduction. Okay, I want to model the conduction flow, and I want to assign a 500-watt number to this block. Okay, I can also, if there is any transient type of behavior, I can do that. I can load from library. Uh, for those of you who are not familiar with transient and what it is, it's in some system, you may have a component ramping up in terms of heat and then become stable, and then it could cool down, and then it can heat up again. So there's all of these transient type of thing before it reaches equilibrium. Uh, as long as you know what that curve looks like, we can define that behavior in here, and we will model the transient condition. Okay, this also includes things like hysteresis effect, and hysteresis refers to the path where you might be following one path when you're heating up, and you're following a different path when you're cooling down. This creates more of a rectangle or hysteresis type of response. We can also take care of that. Okay, so now we have defined the two basic components, assign the material, assign the load. Let's add some monitor points. So we go back to the first one, and I want to add a monitor point. Okay, just click on that. So now that is placed right in the center of the device, but you can move this monitor point to different places if you like. Also, I will add another monitor point to the device here. So just add that. So now I have two monitor points. These are the points that will be probed, and the result will be shown for these points. Okay. What else do I need to do? I need to go to the system environment, and then I need to define some grid structure. Okay. So for the grid, you can specify the minimum, the maximum, smoothing, coarse, medium, fine, and all that stuff. I'll just make this simple. I'm changing it to millimeter, and I'm going to say the maximum size is going to be 40 millimeter grid. Okay. So figure out anything you want, but cannot be bigger than this. Okay. Now, sometimes you may not know what the optimum number is, and that's where parametric sweeping comes in. You can also experiment with the size as one of the parameters. So I've done that, and so I'm ready to run the simulation. That's very simple. So just click on solve, okay, give it a name, a project name, and all kinds of notes in here, blah blah, right? Okay, any kind of thing. And if this is going to be a design that is used many times later, you can save them as a template, so other people can use this later on. Okay, whether you want to save it with the analyzed result or not, or just a structure, and that's fine. So it's not just saving the file away, but you can also use it as template. When you say okay, and here is the analysis, and it's still running. And very quickly, we have two plots, okay? And the first plot on the right shows that we have ran 57 iterations. And at the same time, we're monitoring pressure, velocity, X, Y, and Z, as well as temperature. Okay, so temperature is a red point here. And we've seen that as we run more and more iteration, the solution converges. And convergence is defined as something that's below 10. Okay, when you have a residue of 10 or less, and that's converged. Sometimes your solution might oscillate, okay, might oscillate, and you may have to terminate it before it complete. In this particular case, we reach completion after about 57 iterations. Okay, so the solution has been solved, and we have data for the velocity, pressure, as well as temperature. Okay, And then on the other side, looking at the monitor point, we'll see that when we first start up the system, it's up here at 550 degree, and then it drops down, and then it ends up at the equilibrium state of around 300 degree here. Okay, and then that's the equilibrium point. Okay, so that's the plot. Now let's look at the visual editor. So we bring this one up, and now we see that structure of the two pieces that we have. And first of all, let's change some unit. Result, we will change the scalar field. We're going to be looking at temperature. We're going to say, make it an auto range for me. Okay. We also have the ability to clip to the min and the max. And this is very useful because if you have a big system with many components anywhere, how do you know where the minimum and the maximum temperature is? Click on that, it will show you right away. Okay. So here we define the range, and here we will use a surface plot. Okay, so here is our result. Okay, you can spin it around. You can also probe at this location is 309 degree, 291, and I can actually spin it on the back and look at things over here. Okay, and I can just spin this around and all that stuff, looking at things. We can also do the surface plane cuts and all that stuff, but I'll show you that later. So the point here is to get from scratch to modeling something. It's very quick, very easy. Okay. So there's a question from the crowd. How does radiation is measured in this system? So you same kind of thing. You will specify the environment as with radiation. There's a factor for the radiation, and your measurement is still back to the degree, right? Okay. So let me see here if I can show something. So here we have like radiation off. Okay. You can set more stuff in here. Okay. So that's just a quick demo to show you how you can set things up. So let's do a real one where you can model a real system. So let's do a new analysis. Okay, so now we're in a new project. Okay, so the first thing I want to show you is how you bring the mail off. Okay, how you bring the EDA bridge. Okay, so now we click on the EDA bridge. So this window comes up. And what we need to do is we need to load, import the file in. So when you bring in the PCB, if you're using standard PCB tool out there, Cadence, Mentor, we can generate the particular flow EDA file you can bring in. Or we can bring in ODB++ or IDF. Okay, so we bring in the flow EDA, and we'll pick that board file. And here you have it, right? So here's your board. And so let's look at the modeling level. So right now it is blue, which means all of these are modeled as simple components. Okay, we will go through and assign these in a bit. But right now, all of them are simple components. What you, next step you want to do is you want to filter out some components that are not thermally significant. So for example, all these resistors and capacitors, unless they are RF type, they have almost no significance in the heat from a heat standpoint. Things like connectors, right? These are passive; they don't generate heat. Okay, they help with relieving heat in some cases, but for signal connector, those have no contribution whatsoever. So the way to do that will be to do some filtering. Okay, so I will select filter component, and I will say anything that is less than this length, any height that is less than this, any component that has 0 watt, or less than 0, or any component with an RCL, resistor, capacitor, inductor, or connector. Any reference designator containing these names, please filter them out. Okay, so now you can see those white boxes, right? These have been filtered. So these are insignificant for me. So the next step is to bring in the component that are significant. Okay. So for that, we'll bring in, uh, we will swap these components with the library that we have. Now, over time, initially your library will not contain much, but over time you will have components in here. So for example, you may have a component for the Intel CPU, you may have a component for some FPGA, blah, blah, blah. In this design, we have 4 components, okay, that are already in the library. So what we'll do, we'll say, uh, look through the devices in here and look for matching names and matching description and replace those components with the model that I have. Okay, so we say, okay, now you look at this, we will see that first the filtered components are down here, and the simple ones are the ones that we don't have models for, and those are not really significant. The one that is really significant is being called detail model, and that we have. And for the other ones, we have a thermal resistor network or a two resistor model. So for example, you look at this guy, U24, and you will see that the component type is a two resistor model. And here are some parameters of the junction to case and junction to board resistance. How do I get these numbers? Pretty easy. What you do is you go to here and you will bring up, the data sheet, for example. So let me bring this one in here. So here is the data sheet of an Altera device. Okay. And what you need to look for is to go down into the thermal resistance section, and pretty much all the chips out there in the data sheet, you will find these numbers. You will find the definition for theta JA, theta JC. So JA is junction to ambient, JC is junction to case, and JB is junction to board. Okay, those are the definition. And here is the table that shows those numbers. So we will need to use theta JC, these number, and theta JB, these number, depending on the package that you select, right? So those are the number that you can use um, for these, and you will enter those right here for the two resistor case. Now for the detail case, we already have it, so there's no need to do anything here. Now one thing to note is that if you do have a detailed model, you can actually probe and look inside the package. You can look at the die temperature if you want to, okay? All right, so what else can I do here? I can also add, look at the traces, the layers. So look at the stack up. So this board has 6 layers, okay? So I can select layer 1, for example, and I can see that the percent of copper coverage is about 12%. So that looks like a signal layer. Layer 2 is also a signal layer. Layer 3, I have 87%. So that looks more like a ground or plane layer, okay? So what is most significant is really the top and the bottom layer. That's where it radiate heat out, and the bottom is same kind of thing. The internal layer all are also significant, but not as much as the top. So look at the top layer, and we'll do a process. Okay, and this is what it looks like. Okay, let me just make that bigger. So show. So that's what the traces look like. And what we want to do is we want to see the effect of these traces, but we don't really want to calculate every single twist and turn and location necessarily. That can be a huge time penalty. So what we'll do is we'll create these patches. Okay, you can look at the effect of trace heating if you want to, but you don't necessarily want to do that for all the traces. Okay, that doesn't make sense from a practical standpoint. All right, so how do we do that? So we can create these copper patches. You want to be more detailed, or you want to be more coarse, okay? So let's say we are about here. Okay, so those are the patches, and then how many, what kind of conduction band. So we kind of select, some parameters here and say create patches. And what that does is now that layer has these copper patches that can conduct the heat to different places, and you get a good idea of how the heat is flowing on the top layer. Same thing for the bottom layer. We'll do a process, same kind of thing, create patches. And so now we got all these patches. The board is still there, but on the first top and bottom layer, it's a little bit different. Excuse me. And so let's suppose if I want to add a heat sink here. How do I do that? Pretty easy. Just click on this guy, and now I have a heat sink there. And let's see over here. And how do I change parameters of these heat sink? Pretty easy. I go in and I say, okay, I want to change the width to 40. I want to change the length to 40, for example. Okay, and the size changes. I want to change the number of fins from 7 fin to, let's say, 16 fins. Pretty easy. So now you can see, that 16 fin. So there are more things you can do in here, whatever. Once you're done, you say transfer this assembly, transfer and quit. Okay, we're not going to save this. So what happened now is now we have that component in here. Okay, and the visual editor will show that, yep, there's my board. I just made that board. Okay, so that's how you would bring in a PCB. Okay, so next thing we'll show you is how to do the mechanical import. So I will launch the FloMCAT bridge. Okay, and then we'll bring in all these formats here. We'll look at the SAT format, and that's what I have. But basically, there are support for SolidWorks, Cadia, ProE, STL, IGES, step file, whatever. So SAT, we'll bring this one in. So here's my mechanical box. Okay. What I'll do next is I will need to work on it, one layer at a time. So I will select the top first, and I will make that the top piece. Okay. So nothing else, just that top piece. And notice that I have these rounded corner, as well as the venting hole have all these rounded case, thing here. So I need to simplify that while preserving the free air ratios. I'm not changing the behavior. I'm just re-representing this whole piece as a different thermal model. So how do I do that? I need to do a global simplify, and I would say remove all the non-planar faces. Okay, so things that are curvy will be straightened up. Okay, so now you can see that it's being changed, and then we'll do a dissect the body. And what that means is now it's going to look at the component, and it's going to choose whether to use prism components or tetrahedrons or sloping blocks or cylinder to represent the structures of this, and it will create as many as it needs to accurately model these structures. So I said, okay, and now that piece is complete. And then we'll just say transfer the assembly on the other side, okay? And you can actually seeing it right here, right? So the visual editor, now we have that big piece. And so that's one piece. Now let's go back and do the other ones. If I can find it here. Okay, so make this big. So now let's reset and let's pick the bottom piece. Okay, bottom piece, do the top, do the same thing. Okay, close. Notice it took out that hole for the fan, and that's okay because later on when we put in the fan, we will recapture that location back. So dissect, same kind of thing. So move this over So now we're done on that. Now let's look at the PCB. Okay, so this was a temporary PCB. It's a placeholder. It's not a real PCB, but it contains the exact location as well as the mounting hole location. We need to capture that. So we need to translate this guy too. But we'll replace that with a bounding PCB. This is a temporary placeholder. Okay, so now that's done. I'm going to transfer it over. And now here's the mounting hole, okay, for the system. We'll replace that with a single object. Okay, and then we'll move it over. Okay, so that now I'm not too concerned about the screws here. I can if I want to, but I'm not too concerned about that yet. Next to do is just capture the fan. So select that and say replace that with a single component and call that mounting fan. Again, it says a temporary location placeholder for the fan. We will put in the correct fan later. I'll say OK, close, transfer over, and the rest I'm not too concerned about. I'm not modeling the spinning of the fan here. I'm using the fan as a component. Okay, so I'm gonna say discard, go over here, bring up the visual editor, and now I see my complete box. Okay, and I can visualize this. Select one of this guy, select that, and make that a wireframe, for example. Now I can actually see what's inside, location, fan, stuff like that, along with my real board. Okay, so how do I do? What I do next? So what I do here is go over here and say I want to realign the real board to the placeholder. Okay, so I'll make this window a same window and look at this structure right here. Okay, so here is the placeholder PCB. It stands right here, and here is where my real PCB is. I need to move this guy down here. To do that, we rotate and we just zoom in and we select this and we just put it down right here. And then once that's done, I can deactivate the other placeholder PCB by just clicking hide it. Okay, so how does that look like in my real system? So in the real system, here we have that box, select the top, make that wireframe, and now we have that PCB perfectly aligned to where it's supposed to be. Okay, so that's that manipulation. And then let's see, we will need to put in the fan. Okay, so here's the fan. So I'm going to select this window. I'm going to make that big. Do that right here. Select that fan right here. Okay. So to do that, let me just go ahead and bring in a real component from the library. And to do that, I will invoke the library and go to here and say clear filter. And I'm going to go into the fan side of thing, axial fan. I'm going to be using the PAPST, and I will use the 412 fan, and all I do is just drag and drop it into this assembly. So now this assembly has two fans in here. Let me turn off the library, zoom in a little bit, and so this is the exact location of the fan. It is a placeholder. This is the actual fan, and what I need to do is just move it down here like that, and it's done. Okay, so it's lined up from that end, but it's not quite correct yet because let me just take this off because the real fan's on the other side and this fan is just right here, so I need to realign that again. No problem. Go here and let's look at this window, make that big and zoom in a little bit here. So first of all, the real fan is pointing, it's not in the right location. And so I need to move that. Pretty easy. Select this, and I just need to move this over here. Okay. However, it is blowing in, and I need to blow the air out. So how do I do that? Pretty easy. Just rotate that, and I'm done. So I need to deactivate the other fan. Okay. So there you go. Now that is done. And look at the visual editor. Now we have the correct fan in place, the PCB in place, all that stuff. Okay. And I continue to, go through all of this stuff. Um, I can also go in and set the grid, meshing, command center, and all that stuff, which I won't have time to show you. So that is really the process. What I'll do next is to load a pre-solved results. So you can see how it works. Projects, we will import project. So we'll import a pack file. Okay, and we will import this design. So basically, the time it takes to solve for this model, this design is about 45 minutes. Okay, once you put in, all the fans and PCBs and materials and all that stuff. So what I'm loading here is a completed project with all the results saved um, in the project. Okay, and what I have here is an Intel i7 laptop, quad core, 16 gigabyte of memory with dedicated graphics. Okay, so that's basically your minimum system configuration is something like that. Obviously, the more memory you have, the better. And if you have Xeon processor, it's even better. So here is a completed project. It is sitting on a table, and I can run the animation. Okay, and I can look at things in here, okay, and be able to see the airflow, be able to spin it, rotate, look underneath, and all that stuff. Okay, so um, for example, let me stop the airflow. Let me just go back and turn off the table. So select this table here and say hide it. Okay, and move it over here, move it over here, over here. And let's say I want to put everything into, first of all, turn off the animation, which is the particle flow fan. So turn that off, and I turn on the other off. So you can choose any component and do a air particle animation. It doesn't have to be the vent, it doesn't have to be the fan. It can be a component. Okay, so first I turn all those off. Then I go over here and say, make everything, wireframe. Okay. And what I want to do next is I want to insert a surface temperature plane. And I said, turn it on. So now we have this plane where we can move up or down. Okay. And be able to monitor the temperature anywhere. This is in the Y direction. I can also do the X direction as well as the Z direction. Okay, so Z direction. And every time when I move this, I can actually see through, and I can use the X view, the Y view, or the Z view here. Okay, so you can actually cut through, you can actually cut through stuff here. Okay, pretty powerful. Okay, so now we are over there. Let's see here. Okay, now let's turn this off. Now let's look at the table view. So table view is invoked by clicking this table over here. And now we're gonna enable the details. I wanna see the fixed flow. I wanna see the solid conductor. I can see heat pipe text, whatever is in here. So for example, look at solid conductor summary, and I can look at, for example, this U22. If I click on that, so U22 is highlighted here. Click on this, different things highlighted. on the top. Okay. Not only here, we also highlight um, in the assembly drawing here, right, in the workspace. So with this, I can also export out as a spreadsheet, and I can see the maximum, temperature, minimum temperature, all kinds of things. Okay, so animation, airflow, um, cut planes, all that stuff. That's pretty easy here. Um, I did not have a chance to show you how the command center works, but it's pretty easy to set that up too. And you can go through iterations of analysis. Okay. So there was a question. Can you get the optimum location of the fan? It seemed to be better to be close to the heatsink. You are correct. Um, and not only that, let me just turn this off. No table. Okay. So you are right that the location of the fan is not in the optimal. It should be right near here. And the other thing to notice is the fin, right? In this case, the fin alignment is this way, which is good. If you have the fin alignment the other way, which can be a common mistake, right? The air might not be as good as this way. But yes, you are correct. There are many solutions to this problem. You can move the fan to here, okay? That will be in line with this. You can move the heat sink horizontally, rotate it, and then that will be in line with the vent, okay? And the fan could be over here, but you can't just move the fan around any way you want because you may have a restriction in real life of where the fan can be, where the AC plug might be, so all of that stuff. But to answer your question, um, there isn't one optimum location of the fan. Okay? There can be many optimum locations. And then on top of that, this design has 16 fins. Is that the optimum number? Not necessarily. That could be a 7-fin, 8-fin. It could be the case where the thickness, the material, uh, and you can also have different vents over here too. So this vent here may not be the best location for the fan because you can see through the animation that the airflow is going to be over here, right? We can actually turn it on again, right? And then we can animate that. And so you can see the focus of the air is actually not optimum. It's going to be extracting air from the vent out like this. It's not going through the heat sink, the device. So this vent location may not be the best. Probably be better if it's on this side or maybe on this side. I can also turn on the animation of that. Well, that's just showing the fan going out, so that doesn't matter. So there you go. Right. So right away, once you see the visualization of the results, you will have a lot of ideas of how to fix this. But not being able to see this animation, it's kind of tough to visualize what's going on. Also, how do you know if there isn't any sort of turbulence inside the board, which this one has? So for example, air coming in over here, it hits this and some of it is coming back. It's not going through the chip at all, right? So through this animation, you can now actually see, and then you can see underneath, what's going on. Now, granted, this is a case of a single board in a small box, but if you guys have a design where it's a rack-mounted system, much like those tester, right? You have a lot of boards. You have cable. You have assembly. You have liquid nitrogen. You have all kinds of things in that bigger box, and the ability to see the air particle flowing, including detecting where the turbulence are, is very useful. I don't know if you know this, but in a typical rack mount system, right, the the two boards on the side are the ones that get the most of the heat, and the board in the middle are the coolest one. Now, how much hotter, how much cooler, that require an analysis. And with the parametric analysis, you can decide what the spacing between the boards are, okay, to figure out what is the optimum, spacing of the board in the slot, things like that. So I hope I'm showing you here the basic flows. You get a good idea of how to model, such system. There are lots of variations in your final design. You may not have a fan. You may not have vent. There might be just conduction only. It might be just radiation only. Or whatever. So we can model a lot of that for you. Okay. All right. Apologize again. I always exceeded my time, and I try to respect your time here, but sometimes it just go more. So any additional question from the crowd? Check on the chat window. I left my contact information, kong@edadirect.com. If you like, get the link of the recording and the PDF. And if you would like to see, thank you, Saeed. That was a nice, kind word from you. So if you like to engage and look at your particular design requirement or things that you don't see today, we'll be more than happy to engage and look at your scenario. Okay. All right. And with that in mind, I hope everyone have a good day, and take care. We'll see you again in the next webinar. Okay. How do I